Okay, friends, one more quick video, wrap this exam up and wrap this course up. I bet your heads probably felt like they've been spinning for the past few weeks. I understand, I feel you. I tried to minimize that spinning. I've been wrestling with this ever since the Stat 243 course was consolidated from two courses into one. And it's driven me insane watching students struggle with hypothesis testing over the past couple years as the state has come down with this, this new curriculum. So rather than just try to forge ahead in this last exam, I wanted to look back at the idea of a p-value, which is at the core of hypothesis testing. It's the kind of thing I used to spend 2 weeks on by itself in Math 244, and unfortunately it's been relegated to just over a week. Even though we keep seeing p-values, I mean, you saw them a couple times in your exam, right? But I wanted to make sure as we end up that we actually take one more look at them. And in particular, the formal definition of the conditional probability. It's the chance that you got data at least as extreme as you observed under a given assumed null hypothesis. In particular, I want to look at that at least as extreme as observed bit. That's the part that I really want to focus on, because I think that's the part that confuses people a lot. It's like, why do we have to add probabilities? Why can't we just look at the result we got? Like, for example, this is the one we looked at when we it was our first applied version. We were testing out a flu vaccine. We gave it to 500 people and 50 got the flu. Now, usually 12% get the flu, but in our sample, 10% got the flu, 50 out of 100. Why can't we just look at the 50 out of 100 part? Why do we have to look at 50 or more extreme? So I want to look at that mathematically in the rest of this video. So let's go take a look at that now. Okay, my friends, so we're looking at the exact same kind of, well, the beginnings of the exact same graph we looked at. I guess it would have been week 9, day 17 of the course, where I basically simulated the experiment of giving 500 people over and over again the flu vaccine and then tracking how many of them got the flu. So right now, currently, 53 people got the flu. That's what you're looking at, this single gray bar right here. And what was cool about this is I can re-randomize. Right there, we got 62 people with the flu, then we got 59, then we got 51. And if you remember, as we randomized this in whatever day that was, day 17, I believe, aha, there's a couple. A couple bars showed up that were colored red. And I explained that on whatever day that was. Those were the bars that showed either 50, which is that bar right there, or fewer. What I want to do in this video is explain why we have to look at 50 or fewer. Why can't we just look at the 50 bar? Now, in order to do that, I'm going to need a lot more trials. So I'm going to go ahead and let this thing run and shut up while it runs. And then we'll come back after it fills out. Okay, my friends, I think this is enough data. We've run, I don't know how many trials we've run, but it's plenty. So the idea is I want to break down why we have to add up these red probabilities. Why can't we just look at the single 50 out of 500 result? Why do we have to look at 50 and 49 and 48 and 47 all the way down into the tail? Okay, so the big takeaway is, and this is why I redid this video. I don't know if you noticed, but I redid this video. It looks like the same curve you looked at in week 9, but these values on the vertical axis are percentages now. They are no longer counts, they're percentages. And I did that intentionally because a p-value is a probability, which means it's a percentage. So why can't we just look at a single value? This is the probability value of that single value. It looks like it's about 2.2%. Okay. Now that's pretty small, right? That's pretty small. But here's the catch. Every probability in this curve individually is really small. For example, this is 5% right here. 5% is the cutoff for 5% significance, 95% confidence. If you look across the top, almost every probability in this curve is considered under that. And the ones that are above it are just barely above it. So in other words, even when probabilities are the most common in this sampling distribution, they're still small. Now, that should make sense that all the probabilities are small, because if you have so many options for the variable to be, remember we gave this vaccine to 500 people. That means there are literally 501 different situations. Nobody could get the flu, one person can get the flu, two people can get the flu, up to 500. I'm only focusing on the most common probabilities here. But even those most common probabilities, those modal probabilities, there's so many of them that they individually have to be small so that they sum up in entirely to 100%. So since you've got so many possibilities, each of those individual bars have to have a very, very small probability to make sure they add up to the 100%. So in order to get any kind of a meaningful result from a p-value, you can't just look at one probability, because any single probability is going to look unusual. Any single probability. So what you have to do is you take the sum of the probabilities. And the reason we sum away from the center is because we are looking for that element of surprise that we spoke of in week 9. The idea that that result, if that result surprised us, so would 49, so would 48, so would 47. So these would all be, if indeed, and this is a big if, this is the whole point of the hypothesis test, if indeed 50 out of 500 would be surprising, so would 49 out of 500, so would 48. So you end up summing the probabilities away from the center. So I hope that looking back at why we have to not just look at our data, but at least as extreme as our data, I hope that helped a little bit. So go get the last question and let's get this exam done.